In the last video we considered a stationary point of a function. At a stationary point x0 of a function, the slope of the tangent is 0. The tangent is a horizontal line. That means the derivative of the function at x0 is 0. We proved that the stationary point is a local minimum if the second derivative of the function at x0 is greater than 0. We proved it's a local maximum if the second derivative of the function at x0 is less than 0. And we show that if the second derivative of the function at x0 is 0, if the point x0 is a point of inflection or a min or a local max. So when the second derivative is 0, we cannot conclude anything about the nature of the stationary point. Let's take this example here. We are going to get all the stationary points of this function and we are going to see if they are local max or min. So to get a stationary point, remember, we have to get the first derivative. So at a stationary point the first derivative is 0. The slope of the tangent to the curve is 0. So we set df dx equal to 0 and we solve the resulting equation. And this is a simple quadratic to solve. We get two values for x. One way to determine what type of stationary point we have at each of these values of x is to get the second derivative. So we differentiate this function again. If we do that, we get 6x. Then we plug in turn each of these values of x that we got. So we get the second derivative at root 2. If we do that, we get a positive value. That tells us that x equals root 2 is a local minimum, or there is a local minimum at x equals root 2. Similarly, the second derivative at the other value of x, at the other x value of the stationary point of a stationary point is negative. So that tells us that at x equals minus root 2 we have a local maximum. Now we could very easily decide which of these values of x give us a local max or a min by just drawing a rough sketch of the function. A cubic function has two turning points. So if we work out f of minus root 2, we will get some positive value. If we get f of plus root 2, we get some negative value. Simply because the y value of this point is greater than the y value of this point here. So if we plot these 2 points, we can then say straight away that this must be a local max and this must be a local min without doing any second derivative test. So we just get the x values of the stationary points, and if we plug them back into the function, we will have the y coordinates of the 2 stationary points, and the stationary point with the largest y coordinate must be a local max. Next we have the function cos of 2x defined over the interval between point 1 and 6. To get stationary points we must differentiate this function. So the derivative of the cos function is minus sine, and then we differentiate the angle to give us 2. So we get minus 2 sine 2x by the chain rule. So we set this equal to 0 because we want the first derivative to be 0, and we divide across by minus 2, so we just have to solve this equation here. The sine function is 0 when the angle is a multiple of pi, or a multiple of 180 degrees. A multiple of pi radians or 180 degrees. So we want integer multiples of say pi radians. So that's 1 pi, 2 pi, 3 pi, 4 pi, so on. But of course we want x to be in the range 0.1 to 6. So we look at these values for x. So from this equation we get x equals pi over 2, and pi over 2 is indeed in this range. Pi over 2 is about 3.14 divided by 2. For this value here we get x equals pi. That's 3.14. That is indeed in this range. And the next one is also in the range actually. 3 pi over 2 is actually less than 6. But if we set 2x equal to 4 pi, we get x equals 2 pi. That's 2 times 3.14. That's outside this range. It's bigger than 6. So we're only interested in these 3 values of x that satisfy the equation. So these 3 values of x give us stationary points in this region here. To determine the nature of these stationary points, we take the second derivative. The derivative of the sine function is cos, and we multiply by the derivative of the angle, which is 2. We have this minus 2 giving us minus 4 here. And we plug and turn each of these values in and look at the sign of the values. So we just work out this quantity at pi over 2, at pi, and at 3 pi over 2. If we plug pi over 2 in, we have minus 4 times cos of 2 times pi over 2. Well, the cos of pi is minus 1, so we get plus 4, which is greater than 0. So we just compare the second derivative to 0. If it's greater than 0, we have a local min. For the next example, we have pi. The cos of 2 pi is the same as cos of 0, which is 1, so that's negative. So the second derivative is less than 0, means we have a local max at x equals pi. For the next example, we have cos of 2 times 3 pi over 2, or the cos of 3 pi. The cos of 3 pi is the same as the cos of pi, or the cos of 180 degrees, which is minus 1. So we get a positive result here, and that tells us that at x equals 3 pi over 2 we have a local min. So here's the picture. We have a local min at pi over 2, local max at pi, and a local min at 3 pi over 2. By the way, the period of cos 2x is 2 pi divided by 2. The period of cos x is 2 pi. But if it's cos 2x, we take 2 pi and divide by the coefficient of x. So 2 pi divided by 2 gives us pi. So the period of this function is pi. So you can see the cos of 0 is 1. The cos of pi is also 1. So over the interval 0 to pi, the function repeats itself, and another 0 to pi. So 0 to pi is the period. Okay, here we have this quartic function. We want to determine the local maxima and our minima, so we need the first derivative to get the x values of the stationary points. Set the first derivative equal to 0. So that's straightforward. So we need to solve this equation here. We just put each factor in turn equal to 0. X squared equals 0 gives us x equals 0. 4x minus 1 equals 0 gives us x equals a quarter. And now that we have the x values of the stationary points, we must get the second derivative of the function at those values of x and compare it to 0. So the second derivative of this is 12x squared minus 2x. Let's plug in x equals 0. We get 0, which means that at x equals 0 we have a stationary point whose nature we do not know. However, at x equals a quarter we get a positive value, and that tells us that at x equals 4 we have a local minimum. Okay, so how are we going to determine what kind of stationary point we have at x equals 0, since the second derivative is 0? Well, we could just go and sketch the function. Sketch this out. If we look at first derivatives of it, however, for values of x that are slightly less than 0, we will get a negative result. So tangents to this part of the curve are negative. And if we look at the first derivative of the function for values of x slightly greater than x0, we also get a negative result. So you could, for example, plug in minus 0.1 into the first derivative. You could plug minus 0.1 in here and you will get a negative quantity. And if you say plug in plus 0.1, that's a value to the right of 0, into this here, you will also get a negative result. So the tangents are sloping down the way for values of x less than 0 and for values of x slightly greater than 0, until we get to x equals a quarter, of course, where the tangent is horizontal. Okay, this type of a stationary point is called a point of inflection. So as you can see, the first derivative is 0. The tangent to the curve is 0. Well, that's the definition of a stationary point. But the slopes of the tangents on both sides of the stationary point have the same sign. They're both negative in this case. So as a reminder, this is the picture that we have. So here we have our stationary point, and on both sides the tangents have negative slope. It's a point of inflection. Actually, this is another type of point of inflection, but this time the tangents on both sides have positive slope. Okay, we're dealing with this situation here.